At the heart of linear algebra is the study of vector spaces. And there's only one vector space that we actually study in this course, and we've been already studying it all along. That is Euclidean space, Rn, the set of all n-dimensional vectors. Now what this chapter focuses on is the study of subspaces of Euclidean space. So in other words, smaller vector spaces that live inside of it. Now what does that mean exactly? That's what this section is going to be about. What does it mean to be a subspace of Euclidean space? Well, before you can talk about subspaces of Rn, you have to first understand what a subset of Rn is. And that's where we'll start. So a subset, and for the purpose of this definition, we're going to give it a name. A subset W of Rn is just simply a collection of vectors in Rn. So take some vectors that all have the same number of coordinates. Maybe if you take a bunch of vectors that have 3 coordinates and you put them together into a collection, that would be a subset of R3. If you take a bunch of vectors that each have 5 coordinates and you put them together into a collection, well, that would be a subset of R5, and so on, right? Now, there's some notation that we can use now to talk about this idea. So the first thing I'm going to say is that if we do have a subset W as above, that some set W, which is a subset of Rn, then we can write it in the following way. So if W is a subset of Rn, then we write W is contained in Rn, like that. So you can read this out loud as W is contained in Rn, or W is a subset of Rn, however you like. This symbol here is referred to as the inclusion symbol. It just means is a subset of. All right, now, well, if this is the case, we can say more then. So I'm going to start by writing that. If this is the case, then every vector, which I'll use the letter U to represent this vector right now. So every vector U in Rn, well, it's either going to be in W or not. So let's articulate that. Either belongs to W or not, right? Because if W is a collection of vectors, that are all in Rn, and I just pick some other vector in Rn, or I shouldn't use the word other there. So if W is a collection of vectors, and I arbitrarily choose some vector in Rn, it's going to either be in W or it won't be in W. One of those two statements has to be true. That's how sets work. So if it happens to be the case that this vector is in W, we have a notation for that. So if U does belong, oops, I was wondering when that was going to happen. So if the vector U does belong to W, then we write the following. We write U is an element of W. We've kind of already been using this notation. This notation is how we say that we have a vector that belongs to Rn. And really it's the same notation and it means the same thing. So this is how you would say that a particular vector U happens to be one of the elements inside the subset W. This symbol here just means is an element of or belongs to. We've mentioned it before, but now we'll talk about it again. Now, on the other hand, if it's not in W, we have notation for that as well. Just write the same thing, but draw a line through it. So otherwise, we write the following. We just write U is not in W. So that's the absolute fundamentals of working with objects in sets and how you can refer to objects that are either inside a given set or not inside a given set. And in this case, we're talking specifically about subsets of Rn. Now, how do you write these things down? How do you talk about them? How do you describe them? Typically, you'll use something called set builder notation. So that's what I have this line reserved for. So we often will write subsets of Rn using set builder notation. All right, so here's an example. So I'm going to write it down, and then we're going to talk about how to interpret this language. So let's say let. So in other words, if I use the word let, I'm just about to to define an object usually, or invoke some sort of meaning behind a symbol that previously did not have meaning in our work. So in this case, it's going to be W, just to keep in line with the convention I've already started. But it doesn't have to be called W. You can call it absolutely anything you like. So let W be the set of all, that's how you read that first bracket, the set of all vectors of the form xy such that, I'm kind of reading these words out as I write down the corresponding symbols, and then we'll go through it once again at the end carefully. So it's the set of all vectors of this form such that, or you can say, you can interpret this colon, the full colon, as satisfying the condition, and then you write the condition down immediately after, which in this case, and for this example, I'm going to say x is equal to y plus 1, and then I'll close the bracket afterwards. So that defines a set of vectors. And in fact, this is a subset of R2. And let's look at why that is the case. There's two main components that I really want you to be clear on how to interpret. There's this part, and then there's this part afterwards. Okay, so on the left, this is a typical how should I word this? Let's say typical form of an element in W. Okay, so that's what that's telling you. It's saying that if you have an object and you want to decide whether or not it is in W, well, the very first thing you must do is make sure it fits this form. So what this is saying is that the objects inside the set W all have to be two-dimensional vectors, right? Because you can see, what have I written here? I've written down a two-dimensional vector. It's got two coordinates. Okay, well, what is the significance of the labels x and y? Is that important? Not really. Not for how you interpret this part. The fact that we've labeled them x and y do not matter. However, when you go on later to now interpret the criterion or the condition that's written afterwards, the symbols that are used to write down a typical form of an element in W are going to be the symbols that are used to state the condition. So the x and y in this condition are referring to the x and y in this form. And we'll talk more about that in a moment. But for now, let me just say the following. This is the criterion for determining whether some vector, I'll just write a vector, that happens to be of the form xy is in W or not. So roughly how it goes is the following. If you have a two-dimensional vector, well, assign its two coordinates to x and y. And then check now whether this condition, or in this case it's an equation, but it doesn't always have to be, that this statement is a true statement or not when you plug the values, the coordinates of your particular vector in for x and y. So let's actually look at some concrete examples. I'm going to write down some two-dimensional vectors, and then we're going to test whether or not they are in the set W. So here's one vector, 1, 0. I've got the vector 3, 2. I've got the vector 0, 0. Okay, and now I'm going to write down the vector 4, negative 4, pi plus 1. See, that's a two-dimensional vector. Both of the coordinates are irrational. That's an irrational number. Both coordinates are. But that's okay. They're as long as they're real numbers, as long as each coordinate's a real number, that's a two-dimensional vector in R2. And then the last two vectors I want to write down. The first one is going to be root 2 for the first coordinate, and then root 2 minus 1 for the second coordinate. And then the next vector is going to be root 3 plus 1 for the first coordinate, and root 3 for the second coordinate. Okay, so let's go through these one at a time. Start with this vector 1, 0. How do we check whether this is actually inside the set W? Well, just take the 1 and the 0, plug them in for x and y, and then see if now this statement is true. So if we plug in 1 for x and 0 for y, what's this equation going to turn into? It's going to turn into the claim that 1, because x is equal to 1, is equal to 0, because y is equal to 0, plus 1. So 1 is equal to 0 plus 1. Is that a true statement? Absolutely. 1 is equal to 0 plus 1. So that means this vector is an element of W. Let's go on to the next one. 3 and 2 are the two coordinates. So plug in 3 for x and 2 for y. What does this equation become? It would become 3 is equal to 2 plus 1. Is that true? Sure. 3 is equal to 2 plus 1. So that means this is in W as well. Now, before I keep going in this fashion, it helps now to think of a more efficient way to approach this. What you don't want to have to constantly do is to constantly now take individual values, plug them in for the coordinates, now test whether each one, when you plug in those values, test whether this equation is true literally. I mean, you could do that in a robotic sense, and technically that is the most formal way to do it. And if you were, writing some software or designing a computer program to do this, and you wanted to make sure it was never wrong and it always came out with the right answer, that's what you would do. You take these values, you plug them in to the two variables, then copy those variables over to this equation and test whether it's true. But as human beings, we can do a little bit better. We can ask ourselves, can this be explained in words, what's happening? Can we explain what the set W is without having to actually refer to the letters X and Y, and we do it without even saying variables? Because if you can do that, then you can answer all these very quick. The remaining 5 questions of these 5 vectors, are they in W or not? You can answer them a lot more efficiently. So that's what we're going to do. So really, what is W? W is, let's say it out loud without saying the words X and Y at all. So W is equal to the set of, that's what this bracket means, the set of all two-dimensional vectors. Right? I'm avoiding saying X or Y. Two-dimensional vectors such that, or satisfying the condition, or with the property that, and then I'm going to state the property afterwards. But how can I state this property without saying X or Y? How can I state that equation? We'll dig a little deeper. What are X and Y even there for? They're to refer to the particular coordinates of this vector here. So why don't we say it like this? W is the set of all two-dimensional vectors with the property that the first coordinate is equal to 1 more than the second coordinate. Say it like that. So W is equal to the set of all two-dimensional vectors whose first coordinate is 1 larger than the second coordinate, right? First coordinate is 1 larger than the second coordinate. First coordinate is 1 larger than the second coordinate. So both of those examples, that's why you know they're in W. What about this one? Is the first coordinate 1 larger than the second coordinate? No, both coordinates are equal. So that is not a vector in W. Next vector. Is the first coordinate 1 more than the second coordinate? No, it's 8 more. In fact, it's way more than 1 more than the second coordinate, right? It's too big, too much larger than the second coordinate to be in W. So that is not in W. What about this one? Is the first coordinate 1 larger than the second coordinate? No, in fact, the opposite is true. The second coordinate is 1 larger than the first coordinate. So it almost works, except they're flipped, unfortunately, so that they don't get to be in. This vector does not get to be in W either. What about these last two? Is the first coordinate 1 larger than the second coordinate? Yep, by design, right? Simply by the way this is written down. Just because it's an irrational number doesn't matter. The point is, if I add 1 to the second coordinate, I get exactly the first coordinate. So that's why this works. This is in W. And then for this one, same thing, right? If I add 1 to the second coordinate, I get exactly the first coordinate. So the first coordinate is 1 larger than the second coordinate. So this is an element of W. So that's the idea. Okay, that's how you interpret this notation. So now, before we finish the end of this page now, I'm going to actually give you the definition of a subspace of Rn, which is quite a bit stronger of a requirement than to simply be a subset of Rn. And in fact, the very first part of the definition is as follows. If you want to be a subspace of Rn, then you better be a subset first and foremost. And if you're not a subset of Rn, you can forget about being a subspace of Rn. So let's go through the definition. So a subspace of Rn is, first of all, it's a subset of Rn. We'll call it W for the purpose of writing out this definition. It's a subset of Rn which satisfies three conditions. So here are the three conditions. The first condition is the easiest to write down, and it's the easiest to check. It's the easiest to work with. All it is it's just simply the claim that one particular vector has to be in W, and that's the zero vector, right? The zero vector in Rn. If W is a subset of Rn, it had better contain the n-dimensional zero vector. That is the vector that has n coordinates, each of which are equal to 0. That's not an option. It has to be in there. And if it's not, if the zero vector is not in W, then forget it. It's not a subspace. And you don't even have to think about the other two conditions, which I haven't written down yet. But if it passes that test, then you'd go on to the next condition. The second condition is that if you've got two vectors in W, so any two vectors at all that happen to be in W, then if you add them together, their result had better also be in W. Okay, so that's the way to say that briefly in ordinary language is just this. Just say that W is closed under addition. That's really what that means. So if the vectors x and y are in W, so if you got though x and y are just two labels that represent any potential vectors that are in W. If you ever can label two such vectors, then if you add them together, the sum had better also be in W. So that is condition 2. So that's just saying that if you take two vectors in W and add them together, the result's going to be in W as well. All right, so let's take a look at the previous example just to illustrate. Actually, no, I'll save that till after. I'll save that till after we finish this page. So, and the third condition, I want to say this first. In ordinary language, this is referred to as a subspace must be closed under scalar multiplication. So here's how it works. If you have a vector x in W and some scalar k, then if you multiply that vector x by the scalar k, the result has got to be in W as well. All right, so those are the three conditions of a subspace. So if you have yourself a set W that is contained completely in Rn and it satisfies all three of those conditions, then it is a subspace of Rn. And really what this means, which we're not going to really get into applications of this in this course, but it is so important I would feel guilty not saying it. What it really means is if you have a subspace of Rn, that means what you have is a brand new vector space. Right? And that's why they're interesting objects to study. We like to study different vector spaces in linear algebra. Unfortunately, due to time constraints, we won't get into too much of that in this course, but for now, that's the justification for why we care about subspaces of Rn. If we get a subspace of Rn, we now have a new vector space to study. Okay, let's look at an example first of something that fails to be a subspace. So let's actually just go back to the same example we started out with. Let's say take W to be the set of all two-dimensional vectors x and y such that the first coordinate is 1 larger than the second coordinate. And my claim to you is that this is not a subspace of Rn. And I just have enough room to finish that. So it's not a subspace of Rn, which means I'm saying that at least one of these three conditions fails. And I haven't told you which one yet. But here's a hint. It's on this page and it is visible right now on the screen. Well, what would n have to be? If this is going to be a subspace of Rn, actually let's be more specific. Let's scratch this out because why you wouldn't say Rn in this case. You would be more specific because the number of coordinates in a typical vector in W is 2, right? W is a set of two-dimensional vectors. So we wouldn't talk about being a subspace of Rn. So pardon me, that was a mistake on my part. We would talk about being a subspace of R2, right? Specifically, we would be specific about what we're looking at. So this should have been R2. Okay, so let me cross that out. So the claim is that W is not a subspace of R2. So which one of these three conditions fails? And to answer that question, look up here. We talked about this already. We said we already concluded that the zero vector, because this is the zero vector in R2, right? That's the vector that has two coordinates both equal to 0. This is the zero vector in R2. So that means, and that's what this notation means. It's whatever n you're dealing with, you're talking about the zero vector that happens to be in Rn. But in this example, we're dealing with R2. So our zero vector is given by this. And we already said it's not in W. So the reason the zero vector, which is in our case the vector with two coordinates both equal to 0, is not in W. And that's, if you're trying to demonstrate that this set W is not a subspace of R2 and you supply that as a reason, you're done. You don't have to say another word. It's already established that W is not a subspace of R2. You don't have to go on and now say, well, I wonder if these two conditions are satisfied. I mean, you could if you care, but you don't need to. Your argument won't rely on it, because all you need to do to show that something's not a subspace of R2, only one of these conditions needs to fail. If more of them fail, then all the better, but you don't need to demonstrate that. But because I want to take an opportunity to really further illustrate what property 2 is saying, and even property 3, let's look at how property 2 also fails, because it just so happens that all three conditions fail for this set. So let's look at a particular example where property 2 is going to fail. In fact, let's start up here. 1, 0 is in W. 3, 2 is in W. But watch what happens if we add them together. 1, 0 plus 3, 2. What do you get? If you add those together, you're going to get, well, the first coordinate's going to be 4, and the second coordinate is going to be 2. Now, is this a vector in W? No, because the first coordinate is actually 2 more than the second coordinate. But it's supposed to be only 1 more than the second coordinate if it's going to be an element to W. So it follows that 4, 2 is not an element of W. And I'm not going to write down long-winded sentences to explain this, but I just want to say it out loud. This is an example of statement 2 failing, because we've got two vectors. Think of these. Let's say this is x, and this is the vector y here. So that's the vector x, and that's the vector y. Then that means this would be the vector x plus y. So that means we found a vector x and y, which are both in W, but their sum is not in W. That's what it means for statement 2 to fail. And we can similarly show that statement 3 fails. All we need to do is find at least one vector x in W and some real number that when you multiply that vector in W by the scalar k, the result ends up not being in W. In other words, this statement fails. That's what it means to show that the third statement fails. Well, you don't have to look too far. In fact, if you just choose almost any scalar that's not equal to positive 1 and multiply this vector by that scalar, what's going to end up happening is it's not in, the result is not going to be in W. Let's try. Let's just take k equal to 2 and then take this vector x to be 1, 0 again. What if I go 2 times 1, 0? Well, the result ends up being the vector 2, 0. And is that in W? No, because the first coordinate is 2 larger than the second coordinate again. So this fails to be in W. So that's an example of how the third statement can fail, right? But in our case, I didn't write too much down for this. This was just some little side observations. Most of my discussion here was just out loud. I didn't write a whole lot down. So we will talk about that idea again before the end of the section, and we'll write things out a little bit more formally. But for now, this is just a casual conversation of how these two statements can possibly fail. But in our case, in this example, we didn't need to go that far because the first statement already failed. So we didn't need to justify that these two statements failed. So that's an example of a set that's not a subspace.